Hi everyone, welcome to another video for the Reproducible Rehabilitation Research Education Program, or Repro Rehab. This is, I believe, now the fourth video in our sort of crash course introduction to R. We've been through some basic steps of R functions, importing data, merging those data into a single master document. And in today's video, we want to talk a little bit more about data wrangling and how we can actually clean data that we have. So we've stitched data together into kind of the loose general structure that we want. But as we look at this data set in detail, we're going to see that there's a few different problems with it. And we want to kind of get it into a tidier data format to make it a lot easier to work with. So before we actually get into R, let's just take a look again at the Repro Rehab repository. So this is cloned from my GitHub repository online onto my local machine. So for me, it's under the Documents folder, then GitHub, then Repro Rehab. The exact location of this folder, on your own machine is going to depend on where you cloned this repository to. But let's go ahead and look in the data folder. Now, in the last video, we took all of the individual subject folders from inside this EEG subfiles folder, and we stitched all of those together into one master data folder called master EOEC EEG. And as a reminder, these data are EEG data, so it's actually the power spectrum of the EEG recording during both eyes open and eyes closed conditions for a variety of older and younger adults. So inside of our file, we have this kind of blank column that just counted the row numbers. We have a file ID, which tells us what the original file name was for that subject's data. From that, we've extracted what their subject ID was, because that was the first 4 characters of this string. We also extracted what the condition was, and that was the 2 characters after the underscore. And then for each person, we have their power spectral density at each electrode. So by power spectral density, if you're not familiar with that, right, what that means is we've taken that EEG signal over time, and we're looking at the power in the signal at each frequency, or essentially the proportion of the signal that is made up of 1 hertz versus 2 hertz versus 3 hertz oscillations. So we have a column that represents the hertz, and then we have columns for each of those electrodes, and inside of each of those columns we have the power at that specific frequency. But as you can see, we have some columns where we have missing values, and as we go down, we actually run into an issue where we have basically 0 power in the signal. Due to the filtering that was done with these EEG data, once we hit about 80 hertz, there's almost no power in the signal anymore, to the point where we've got a lot of rows that just aren't really functional and aren't really meaningful for our subjects, because for frequencies, basically 80 to about 512, I think is where it stops, we just get a whole bunch of zeros. So this works great as like a master data file. It retains all of the individual subject information at kind of the finest resolution. But in terms of a data file that we can work with, it'd be great to clean this up and get rid of some of these redundant rows, maybe create some new columns that represent some of the data we actually want to work with a little bit more. And that's what we're going to be focusing on today, taking this kind of wrangled data and tidying it into a more usable format for our analyses and our data visualization moving forward. So let's come back to our studio now. And so this is script 02 wrangling data from inside of that Repro Rehab repository. The first thing we're going to do is load the tidyverse package so that we have access to the different graphing tools and data manipulation tools in things like ggplot and dplyr. I'm just going to set my working directory to that Repro Rehab folder, and then it's always helpful to use the list files function to take a look at what files are in that folder. And you can see we've got that data subfolder, the README, and the script subfolder. Let's look inside of the data subfolder, and we have 3 things. We have the processed data file, and that's actually the final output of what we're going to make today. So it's already going to be in your repository by default, but that's ultimately the thing that we're going to create at the end of today's video. We have the EEG subfiles folder, And then we have a CSV file, which is the master data file we made at the end of the last video. So that's actually what we want to start with. Let's import that master data file. It takes a little second to read it into R because this is pretty big. It's 45,000 observations of 37 variables. And we're going to save that as an object called data. Next, we can select some specific columns in order to do some of the things we want to work with and just show you how the select function works from dplyr. So let's look first at the data so we can see what variables are available to us, right? Again, we've got that first column X, which just marks the rows, the file ID, the subject ID, the condition, and then the frequency. And then we have each electrode from which EEG data were recorded. And if you're not familiar with EEG data, there are 32 channels in this particular configuration, which are located kind of all around the scalp. Things that have an F in it are the more frontal regions, toward the front of the head. Things with a C are more central regions, which kind of cover the area where the frontal lobe starts to turn into the parietal lobe, around the middle of the head. P are those parietal regions up at the back of your head. Occipital has the O at the way back. And the T would be electrodes, roughly over temporal regions on the left and right sides of your head. So, you can look up a picture that shows you the precise locations of these things. But that gives you a general sense of, kind of what's frontal, central, parietal, etc. And the main thing is we have electrodes from all over the scalp, and we're going to want to work with them moving in our data moving forward. So if we wanted to select just specific rows, we can use the select function from dplyr. And so we've used this question mark function before, but if I want to look up and get the help documentation for a particular function, I can do what we have here on line 16 and look at question mark dplyr : select. And I specify dplyr : select rather than just saying select, because if I do that, you can see that I actually have two different select functions. There's one from the mass package and there's one from dplyr. So if there's any confusion, RStudio is going to prompt me and ask me for which one I want. But in this case, I know I want the select function from dplyr, so I can do the name of the package, the double colon, and then the name of the function, and then it will take me to the help documentation. And select is for subsetting columns using their names and types. And then this help documentation would walk you through some of the finer points of how to use this function. But for our purposes right now, let's just say we want to take a couple variables. So we're going to want to take the subject ID, the condition, the frequency, and then the power from electrode FZ. So the Z line is the very central midline of the scalp. So this is the front and center electrode that we want to look at here. And if I do that, you can see it's going to print it to the screen because I didn't save it to anything yet. I just pushed the data frame through a pipe and into the select function. And I got to scroll back a ways, but there we can actually see the beginning of it. So select took my data frame, which has 37 variables, and it pulled out just the 4 that I actually requested inside of that function. So the other way that I could do this is if I didn't want to put data through the pipe into the select function, I could specify the data inside of the select function itself and just say select data equals data, and then give it the name of the columns that I want. And that's going to work just as well. But pipes are really useful because they allow you to sort of daisy chain your different functions together. So I can pipe the data into the select function, and as we'll see in a minute, then I can pipe those results into some other function. But just to show you a little bit more about how the select function works, I don't necessarily have to name all the columns manually. I can also use the colon operator to select a range of consecutive columns. So if we go back to the head of my master data frame, you can see I've got file ID, subject ID, condition, and then Hertz, FP1, FZ, F3. So an easy way to select all of those columns is actually just to say data select subject ID : F3, and that's going to select all of the columns from subject ID to FZ. So if I use that colon, it's great because it simplifies things. I don't have to write as many variable names, but it is going to take all of them in order. It selects all of the consecutive files. Another handy function is the minus sign. So I can use the minus sign to actually drop a particular column. So if I wanted to drop that first x column, I can push data into the select function and say minus x. And now I have all of my previous columns except for that first column x, and now the data frame starts with file ID. Finally, if I actually want to save the output of this, what I can do is I can push the data through the pipe into the select function and then create a new object. So I'm going to create a new data frame called dat2, and I'm going to assign to it the value of what comes out when I push data through the select function. And in this case, I'm going to drop both that first x column and I'm going to drop the file ID, because I'm not as worried about, what the original file name was anymore. I just want to know what the subject was and what condition it was. And I already have that from the subject ID and the condition ID variables. And now if I say head dat2, I can take a look at the header of this new file, and you can see x and the file ID variables are dropped, and it starts with subject ID and condition, and then I have all the power spectra as I normally would, because dat2 is the same length, right? It has the same number of rows as data, but it has 2 fewer columns because I've dropped 2 of those variables. Next, as we saw with the when we had this open in Excel, we had a whole bunch of values down below 80 Hertz that were effectively 0, and we might want to screen those values out. So a handy way to do that is using the filter function. In much the same way that select can be used to filter out particular columns, filter can be used to filter out particular rows. So again, you can use the help documentation to get more information about the filter function. But if I wanted to push my new data frame, dat2, through the filter function, I could select just the data for subject OA01. And if I do that, you can see it's going to pull out just OA01, but all of their conditions and all of their Hertz, because I'm not filtering on anything else. I'm just saying when subject ID equals OA01, give me those rows. If I wanted to do something a little bit different, I could use this pipe to create an OR statement. So I could say filter dat2 when it's OA01 or OA02. And to make what this is actually doing a little more clear, let me actually create a new object called dat3. So we'll go back here and say dat3 is just when we had data from OA01. You can see that that has 1,024 rows. If now I'm going to say dat3 is all the data where the subject ID equals OA01 or it equals OA02, now you can see I have double the number of rows because I've accepted all the data for both OA01 or OA02. So any row that matches one of those 2 criterion is going to get through, and now this is going to have the data from 2 subjects in it. Alternatively, if now I said dat3 is going to be the result of filtering where subject ID equals OA01 and Hertz equals 0.99, now dat3 only has 2 rows, because when I use that AND statement, coming back over here to print this to the screen, you can see that when I said it has to be subject OA01 and Hertz has to be 0.997, there's only 2 rows in which that is true. And that's when we have subject ID in the eyes closed condition with Hertz of 0.997, and subject OA01 in the eyes open condition when Hertz equals 0.997. So I can, specify a single thing or combinations of or and in order to filter out the data to get precisely what I want. However, on line 40, what we're actually going to do for dat3 is push our data through the filter function to take only those rows where Hertz is less than 30. So we said, it really starts to go to 0 at about 80 Hertz. But if, just for the purposes of this exercise, if we're only interested in data where we have 30 Hertz or less, you can see now dat3 has 2,640 observations. So we've cut out all of the rows where the Hertz was greater than 30, which greatly reduces the number of observations, but we've taken all of the variables from dat2. So just to confirm, what the data look like for DAT3, let's get a statistical summary using the summary function. So I'll say summary, just give me the unique values of DAT3 $hertz. So I'm going to take that hertz vector, which again is hertz repeated for every subject. So what the unique function will do is prune out all the duplicates. So it ignores the fact that, I've got a 0.99 hertz for subject 1 and subject 2 and subject 3. It's just going to keep 1.99 hertz. So essentially this keeps 1 hertz value from all the vector of hertz values. And you can see my minimum hertz is 0.997 and my maximum hertz is 29.91 because again I filtered out everything that was greater than or equal to 30. Or sorry, I filtered out everything greater than 30. I kept everything that was less than or equal to 30. If I wanted a nice easy way to visualize that, I can also use the histogram. But this isn't going to be the most interesting histogram because if I do it, there's one observation at each of these hertz. So it basically just looks like a square. But on the x-axis, we can at least see, all right, it starts at 0 and it ends at 30. So it looks like my filter function worked exactly the way that I wanted it to. Within this new data set, then, we can also not just filter out existing variables, we can create new variables. So within DAT3, which again is filtered to be just 0 to 30 hertz, let's create a new variable which is the average of the frontal electrodes. So I'm going to say DAT3 $frontal, and I'm going to assign to it the value of F3 plus F7 plus FZ plus F4 plus F8, and then I'll divide by the total number of electrodes in order to get an average value at across the frontal electrodes. And now if we look at the head of DAT3 again, you can see I have this new column called frontal at the end of my data set. And each of these values is the average within a hertz across those 5 electrodes. Now, if I didn't want to do this manually by assigning this value to a new variable, I have a few different tools available to me inside of dplyr. One is the mutate function, which allows us to create, modify, and delete columns. The other is the transmute function, which adds new variables but does not preserve the existing ones. So if I want to keep all the variables that I have and add new ones, I can use mutate. If I want to drop all of the previous variables and just keep the new ones that I'm creating, I can use transmute. So in this case, I'm going to want to keep the old variables and just add new ones to the end of my data set. So we're going to go ahead and use the mutate function. The other thing that we need to look at here is something called rowwise as a tool inside of dplyr. Because when I do this mutate function, what I want to do is add F3 to F7 to FZ to F4 to F8, but I want to do that inside of each row. And the rowwise function is a really helpful way of doing that. You can see, in its description, it allows you to group inputs by row and compute data on a data frame one row at a time. This is most useful when a vectorized function doesn't exist. So you don't always have functions that will work nicely with your vectors. They maybe want to sum up the value within a column, right? But actually what you want is the sum of values from row 1 across multiple columns, and then the sum of the values from row 2 across multiple columns. And that's what we're dealing with here. So what we can do by specifying this rowwise argument is we'll make a new version of DAT3, which takes the output of DAT3 pushed through the rowwise argument. The rowwise function. So the rowwise function will specify that everything that comes after this is going to happen within a row. And then we will push it through the mutate function, which is going to calculate new variables based on the existing variables. So this is handy because inside of a single mutate, we can now create as many new variables as we want. And in this case, we're going to create a frontal, central, parietal, and occipital average, where we take the mean, so that we'll use the mean function, and then we'll give it a vector of column names. So we'll say C, F3, F7, FZ, F4, and F8. Then within our mean function, we'll also say na.rm equals true. So if for any given row, if one of those happens to be blank, we are going to ignore it in our calculation of the mean, and that's going to then adjust the denominator, right? So for instance, if F7 was blank, we should only divide by the 4 rows that we have, or the 4 columns that we have, not 5 columns overall. So by specifying the function this way, we can actually have a really smart calculator, which is going to look at the available data in each row, right? So at each hertz to calculate the mean based on the available information. Then for the central electrodes, we do the same thing, but we're going to change the columns that we want. Oh, whoops, and it looks like we have a typo here actually on line 56. So let's go ahead and change that to CZ because I want C3, CZ, and C4. Similarly for the parietal electrodes, it looks like there's a typo here because I want P3, P7, and PZ, P4, and P8. So we need to fix those in order to make sure that those are grabbing the correct columns. Occipital has fewer electrodes available. There's only 3, right? But we'll take O1, OZ, and O2. So now if I put my cursor up on line 56, press Control Return, right? That all runs. We don't get any error messages. But if we actually wanted to see what we just did, let's actually say head dat3 and print that to the screen. And now, because this is a tibble rather than a data frame, which is the default kind of data type coming out of dplyr, it doesn't actually print all of our columns because they don't all fit on the screen. But you can see down here at the end, we do have something called frontal, something called central, something called parietal, and something called occipital. So now we've successfully created those columns. If we wanted to see how it lines up with what we manually calculated before, we can plot the capital F frontal, which we created by hand, against the lowercase f frontal, which we created using the mutate argument. And you can see that the values are obviously different, and we have one person who's a pretty big outlier on both of these things. But there's a nice linear relationship here because these things are perfectly correlated. And we're getting exactly the same calculation from our mutate argument using more efficient code than what we would have gotten if we were doing our manual calculation over and over again. We can check that also using the core function. So we can use core to get a Pearson's correlation between the capital F frontal vector and the lower f frontal vector. And we can specify how we want to handle missing observations. So in this case, we will only use complete observations and drop any cases where there's missing values. And you can see they are indeed perfectly correlated. So now that we've filtered out the rows with the frequencies we don't want, we've calculated some nice summary statistics that tell us about the mean power in the frontal region, the parietal region, and the occipital region for each person. What we can do now is actually subset some of the data in order to drop some of the columns we're no longer that interested in. Because again, we're really interested in the power on average in the frontal, central, parietal, and occipital regions. We're not as worried about holding on to the exact values in F3, F7, FT9 anymore. So we can create a new data frame, which I'll call DAT4, which will take the value of DAT3, pushed first through the select function. So I'll select subject ID, condition, hertz, frontal, central, parietal, and occipital columns. And then I'm going to push that through the mutate function one more time to create a few new columns. One will be called log hertz, which will be equal to the natural log of our original hertz column plus 1. Then we're also going to take log frontal, which will be equal to the log of the frontal power, log central, which is equal to the log of central power, log parietal, which is equal to the log of the parietal power, log occipital, which is equal to the log of the occipital power. And actually looking at this, I'm going to go ahead and I'm going to drop that plus 1 because I should either add that in for all of them or I should add that in for none of them to make sure that they stay on kind of the same scale. But just as a reminder, when you're taking the natural log, if you would take the log of 1, it goes to 0. But I don't think and if you take the log of 0, it goes to negative infinity. So one of the things you can always do is add a plus 1 at the beginning to make sure any zeros now take the value of 1. When you take the log of them, they go back to 0. But we don't have any values that are actually 0, so I don't think we'll get any negative infinities. So I don't actually need to include that plus 1 here. So let's go ahead and run this code. Looks like it runs without any problems. Let's go ahead and just take a look. So you can see, all right, we've got our hertz, we've got, the frontal power, central power, parietal power, occipital power like we had before, and then we have our mutated variables. Hertz, right, the first value of 0.997 is a negative value when we log transform it, which makes sense, because if this was 1, the natural log of 1 should be perfectly 0. This is a little bit less than 1, so the natural log of that value is a little bit less than 0. So this looks like our log transform has been implemented successfully. And the next thing that we can do is just export this process data so that we can have it in a workable format moving forward. So I'm going to set the working directory to our data folder, and then I am going to use the write.csv function to export this most recent data frame we made, dat4, and I'm going to export it as data_processed_eeg.csv. And then when I do that, I can come back to the data folder. Here we have this data processed EEG. It should have a timestamp that matches on your computer whenever you actually use the write.csv function. If I open that up, you can see, all right, I've got my subject ID column, my condition, and my hertz. Critically now, though, right, hertz cuts off at 30 hertz for each condition, and then I go on to the next condition, right? And so then I'll have 30 hertz in that condition, and then that's going to cut off, and now we'll go to the next subject, right? Because I have 2 conditions per subject, 30 hertz per condition, and then now we're moving on to the next subject here. Similarly, in my columns, I have not only the sort of the raw values that I wanted, hertz, and then the average frontal, central, parietal, and occipital values. I also have log hertz and the log of the average frontal, central, parietal, and occipital values. In the next video where we're doing data visualization, we'll show you a little bit more about why we're taking the log of these values. In short, it's because we get some very strong skew in kind of the raw space of the power spectrum. So when we put it in log hertz as a function of log power, we're going to get relationships that look a lot more linear, and they're therefore not only a little bit easier to see, but a little bit easier to statistically model. But as long as you've got this processed EEG file, you're good to go for now. And in the next video, we'll show you how to take all of this data we've just been tidying up and create some great visualizations to understand the data better.